comments if you have any questions about the tutorial. Anyone has any specific question on the tutorial sheet that I uploaded? Yes, no? All good. Okay, great. So if this is the case, unless there is any question otherwise, because especially the parts that we covered, the varial equation, these things, just direct implementation. And keep in mind that the method should be clearly mentioned in the question in case such a question was given. Remember, you have an assessment next week. I will confirm it to you maybe today or tomorrow, but most probably it's going to be only in the parts that we did not cover, starting from 2.3 or 4, I guess. Sorry, chapter 3, 3.3 onwards until the end of the chapter. And it's going to be multiple choice questions only within a time frame. You have to solve problems, choose the correct answer, and go ahead. And this is the way, actually, and it might be like shuffled so that we can minimize the copying as possible. So I'm a very transparent person, mentioning the strategy and the techniques clearly, so that you don't face any issue while solving. طبعا, apart from the fact that you don't know what are the questions. Zin, can I then, in this case, can I continue the story of today's morning in chapter 4? It is your duty to solve the questions, and I give you already 1 full week extra to solve the question. So I think I did more than enough. Zin, if this is the case, let me just go and continue the story. If anybody has any issue, let me know. Meanwhile, yani, you all okay? I want to see the okay so that I can continue the story. Okay, thank you very much for your response. I think you are almost happy so far. Okay, the ladder of today's morning was that we reached to a stage where we are able to calculate all delta H naught or standard heat of reaction, but provided that the temperature was 298, and that could be formation or can be combustion. We had no problem with that. We explained the formation and we explained the combustion. Here in section 4.6, I will talk about what if the temperature is not 298. Which happens, it can happen. يعني مثلا, I can give you A plus B, give me C plus D. In the industry, the temperature of the reaction was not 298. And don't expect that you will get 298 everywhere. Of course, that is not possible. So how to deal with this scenario? Let me just explain the story from the beginning. Here, we have a reaction. I did it before, it was A plus B, give me L plus M. Here it is same, but I just put it as A1, A2, A3, A4 as reactants and products. And then I put the stoichiometric. Look at that. It is the stoichiometric number, but I put absolute for it to be stoichiometric coefficient, because the absolute is a stoichiometric coefficient, as you can see here. While the value without the absolute, it is the stoichiometric number. I hope that's clear for you and for everybody. Sorry. Okay. All right, so what we are going to do, we need to know how can we deal with such a case. Okay, now I will change the temperature and see what will happen. طبعا Smith started talking about so many details here. Trust me, I can explain all these details while I'm presenting. But you all know at this stage that to calculate delta H naught, I need to know the delta H formation, provided that the stoichiometric number is given for each. And that's, you know it. If I will apply it on the equation above here for the formation of ammonia, you all know that the constituent element here, it has no delta H naught formation. So in this case, you go to the table and it is 2 times delta H naught formation of ammonia there will give you the delta H or the standard heat reaction for that process. So let's your terminology be precise. We have something called standard heat reaction and we have standard heat formation, which is related to each individual element. طبعا the standardized condition means I have 1 bar, I have, if it is gas, then it's ideal gas, if it is liquid, then it's pure liquid, if it is solid, then it's pure solid. It is function of temperature. Why function of temperature? Because I do need to specify, is the temperature at 298 or it is at different, but keep in mind that it is function of temperature. So, to derive the formula for what to do or how to modify it, I will start with the original equation of delta H. طبعا DH is equal to CBDT. The only thing I did here is that I replaced the H with the standard. I put the standard just to remind you that here we are working at standardized condition. are working at standardized condition, but the temperature may change. This is the idea. Then, what if I repeated this on the reaction, or I applied this on the reaction? If I want to find the summation as a delta, then it's going to be delta a summation of stoichiometric number to dH. In other words, I want to apply this on each of them, then to find the over delta H of the process. If I did this on the left side, I should do the same on the right side. And that is simply stoichiometric number, which is going to be same in both sides. In other words, the equation will still be valid. خلاص? Remember that those are numbers, stoichiometric numbers, those are numbers, يعني constant values, and I can place them anywhere. يعني I can just put them here. So because of that, I just put them, because I can move them anywhere, I just put them inside. So it is stoichiometric number into HI, and each one I multiply by its stoichiometric number, and then I will get the equation as it is. So it's only a number, so I have the freedom to put it either inside the differentiation or outside. Like when you say 2dx or d2x, it's the same because 2 can be taken outside the differentiation. It's a constant value. So here I had this as a number, and same thing for the summation. I put a d summation of stoichiometric number hi, and same thing here. So this is the equation I have. And let's think about it. Haven't we said in 9 o'clock lecture that this is simply delta H naught? Because stoichiometric number means what? Means positive for the product, negative for the reactant. It means the product minus reactant. So this is delta H naught, basically. So if that one is delta H naught, then this one is delta H naught. Then I have to find out a way to get this. Do you remember? Or no need to remember. What I did, I just replaced this stoichiometric number with delta H, as you can see. The D will stay as it is. I didn't do anything with it. Here, I will use the same convention. Same convention. Any summation stoichiometric number into a property will be delta of the property. I will do the same here. Any stoichiometric number into a property will be delta this property. You can see? So that's why I put delta here for the same concept, same phenomena that I used it for H here. Forget about thermo. Think about it mathematically. Mathematically, if I want to integrate here, how can I integrate? This is going to be integration. If I have dx, how can I integrate it? It's going to be integration from x1 to x2, correct? So same thing here. If I want to integrate it, it will be integration from what? From delta H naught, okay, to another delta H naught. Okay, just give me 1 second, guys. I think somebody's knocking the door. 1 minute. Okay, so what I'm doing here, I'm just integrating from one delta H naught to another delta H naught. Doctor, what's the difference? This one here, x1 and x2, we know that this is one x value, this is another x value. Here is the same. Now H, according to the previous slide, let me just, well, maybe I don't have to go to the previous slide, but I already mentioned that this delta H is a function of temperature. So in other words, I'm moving from one temperature to another temperature. This is how it is. Why, Doctora, you are doing this? Because previously we talked about delta H naught at 298 only. Now I want to see what would be the effect if I change the temperature from one temperature to another temperature. Okay, so that's for the left-hand side. Before I continue, I just want to make sure that everybody got this idea because it's important to proceed. Anyone has any issue in understanding that concept? You all okay so far?
Victor, can you repeat?
Who is this?
Arwa.
Okay, Ali, it's clear with him. Who is that?
Arwa.
Arwa, tell me Arwa, what is your question?
Can you repeat the question?
I repeat the integration, starting from the integration or from before?
Before.
Before. Okay, starting from here maybe. Okay, let me remove all that then, and I will repeat. I know this part is not easy to understand. If you did not get it, then I have to repeat it. Arwa, did you understand why I replace stoichiometric number HI with delta H naught?
Yes.
Okay, so that's clear for you, right? Is it? If you agree with this concept that the stoichiometric number into any property is delta, then I will do the same here. Stoichiometric number into any CP is delta also. So if you are happy with the left side, then you should be happy with the right side. You cannot contradict yourself. You are happy with both in this case. الحين we'll look at it from math point of view. How can I integrate? Because you can see it's D on the left side and D on the right side, يعني differentiation on both sides. I need to integrate both sides. Integration of that, it's supposed to be from one limit to another limit. And if it was dx, then the limit of integration is x1 to x2. Here, d delta h, then the limit of integration is delta h naught 1 to delta h naught 2. So how they are different? Because they are changing with changing temperature. You can call it delta H1 and delta H naught if it's confusing, but I just want to tell you that they are different because one delta H is at a temperature, the other delta H is at another temperature. خلاص؟ أروى, clear so far?
Yeah.
أروى? Okay, good. And then الحين with the other part, what do I have? I have integration of CP dt. And then there is delta there, but let me just clarify. If I did integration of CP dt like this, how did we do the integration? Remember that the CP is function of temperature. How we did the integration, I will remind you. We put divided by R, multiplied by R, and then we said that integration is equivalent to CP mean H delta T. This is exactly what we did because I need to find a mean representative for this integration. صح ولا لا? Is that what we did last time? Yes, right? I want to see one yes at least. One yes, please. Okay, great. So according to that, okay, I have many yeses, that's wonderful. So according to that, all what we had here, what's the difference between this and that is only the presence of delta. يعني, if I'm going to modify it here, okay, I have delta over there. So in other words, my result will be with delta. Best, that's it. Oh, okay, maybe still early to show you this magic equation. Then, so what I have here, I have delta CP mean H delta T, and I will explain the delta here means what later. Okay, but according to the math here, delta is there. And here, according to what I have here, I have integration. Now when you substitute here, it's gonna be x from x1 to x2. يعني x2 minus x1. This is how you do it in math, right? If I will apply the same thing here, it's gonna be delta h, because instead of x, I have delta h, so it's delta h naught t. I will call it that one t, not t too, because I have t naught and t. Delta h naught t minus delta h naught t naught. يعني if I want to find delta H naught at any temperature is equal to delta H naught at T naught plus this term. Wow, that is very useful equation. Let's look at it from thermodynamic point of view and explain it. Doctora, what this equation means? It simply means that if you want to find, listen carefully. If you want to find the standard heat of reaction, okay, I'm just going to use the highlight or the laser pointer. If I want to find the standard heat of reaction at any temperature, then you have to calculate the standard heat of reaction at the reference temperature, which is what? It can be 298 because I have table for it. So you will calculate this for the reference temperature that you have, يعني for the delta H that you already have its table. Plus correction, I will call it correction. شنو يعني correction? You correct for this value by adding another heat. What is that other heat? CPDT. But what is that CPDT? It is delta CP delta T. Okay, يعني the standard heat of reaction at any temperature, it is the standard heat of reaction at reference temperature plus a correction term that will consider what is happening as a result of changing the temperature. خلاص? So that's basically the idea. And then, if delta is there, what does it mean? Each delta, يا شباب, each delta means it is the what? It is the stoichiometric number into the property. It is the stoichiometric number into the property. And to show you that clearly, here, the equation that's written there, it is same as the equation written here. But he just here put it to you without showing that it is mean. Actually, it is mean. And the only way you have to do it, or the easiest way you have to do it, is to get it through this mean. Okay? الحين, talking about the delta means what? Okay, now I will just remove everything here. Okay, so that's basically the conclusion. And as I said, that last term is here is the mean CP delta T. That whole term. And TP for what? For the delta. CP mean H. زين. الحين back to the delta. The CP mean itself, when we talked about it, last week's lecture, not tomorrow, this morning, but the lecture before, the CP mean itself, it was, if you remember, R into A plus B naught. It was a long equation. Again, you don't have to memorize it. Okay, it's long term. But what I have here, I have exactly the same equation, but it's not A. It is delta A, because I have delta here. It's not B. It is delta B. زين. يعني شنو? يعني I don't have only one A. I don't have only one substance. Remember, here we are dealing with reaction that has products and reactants. يعني the A that I want to find, I have to consider A for each species and its stoichiometric number, and I do the math. Delta A. Same thing with delta B, same thing with delta C, same thing with delta D. Then I substitute in the equation. Because of what? Because of the presence of delta. Okay, so this is the equation, as I said, with the mean, but the delta needs to be dealt in other way. I will show it to you in the next slide to make sure that it is so clear for you. Here is the one. And the main CP, again, you may not have to use those two equations, because that will solve all your problems. Trust me. Unless you want to use programming, then those equations, the first two equations will be needed. But I can tell you that the CP mean can be calculated simply using this equation. And then to find out delta CP mean H delta T, you will just multiply it by delta T. As simple as this, which is what? Which is this second term here. Okay, but to make it clear that how to calculate CP mean, you have to calculate delta A, delta B, delta C, delta D. زين. How is this? Victoria, how is this? Because to calculate delta A, يعني مثلا you have the reaction. Let me just write it as I don't want to use A and B, because here we have A and B, so it will be confusing. I will just say X plus Y give you L plus M. Okay, so this is the reaction. Okay. To find delta A means what? Means you have to go to the table which consists of A, B, C, D. Remember that table? There is an appendix, a table, appendix B, that shows the A, B, C, D values. And then the A, B, C, D values for what? For X, Y, L, and M, 4 substances you have. And to calculate delta A, it is the summation of the stoichiometric number into AI. يعني you will get A of X, A of Y, A of L, A of M, and then you will substitute here. That stoichiometric number, you already have it as number there. Don't worry if you did not get the idea 100%. I will solve full problems actually, not a problem, so that it shows how can we apply such a mechanism. But it's not only 1A, 1B, 1C, and 1D. Why it is not? Because I don't have one substance here. I have maybe 4 substances or 3 substances. It depends on the reaction. Okay, so that summarizes how can I get the delta H at a temperature that is not at 298. How can we do so? We have to find it at 298, then correct it by adding additional term. And just to have this thermodynamic meaning, and you need to understand what's happening here. It's like I'm finding delta H at 298 plus a term, whether it is higher or lower than this term. It depends on delta T, positive or negative, because CP mean is always positive. Remember, that's mean value. But it will be positive or negative, depends on whether T is higher than T naught or lower than T naught. But at the end, I'm correcting the delta H at 298 with another term, as you can see there. So if that is clear, then I will move to solving a problem. Let me know if you have any question. Anybody has any question before I proceed? You all okay? So the kink equation for the temperature dependence is this. This one is the most important, or the equation that you are going to use for your calculation. Okay, I can see here in the post that students are okay. I think Ali answered. Can I just see some more? You have no problem? Okay. All right. So I can see now students started to say yes. So anybody want to say anything before I move to solving the problem? And see. You all okay? Hello? Okay, great. So if this is the case, I think you are ready now to solve our problem. Let me clarify what we are going to do here. And let me clarify, this is example 4.6 from your book, but I modify it to make it clear in terms of a presentation and to be like direct implementation, not direct, but implementation what we explained so far. What we had here, we have methanol, and that methanol is synthesized via the exothermic reaction shown below. So I have here exothermic reaction where methanol is synthesized. Synthesized means it's produced. Okay, so or it's manufactured. Okay, but produced in a chemical way. So we have the synthesis of methanol. What they say that the reactants are fed in stoichiometric proportion. What stoichiometric proportion means, if you remember from chemistry, stoichiometric proportion means it's based on the stoichiometry. In other words, the reactants fed as 1 mole of CO with 2 moles of hydrogen to give me 1 mole of methanol. This is basically the idea. I have a message that I want to say. From now onwards, you will highly need to use Cheng triple 1 material balance. If anyone has deficiencies or weaknesses in this part, please go and study it. That is Cheng triple 1. It's not my duty to explain Cheng triple 1 again here. So make sure that you know how to use extent of reaction and atomic species balance to calculate the masses, okay, or the mass flow rates. Why? Because I will need it here, and I will show you later on when I will need it. But today's lecture, I think you will be fine. You will not need it because we don't have percentage excess, we don't have percentage conversion, nothing of those in this example mainly. Life is easy here that I have the reactant fed in stoichiometric proportion. Stoichiometric proportion means that based on what I have in the stoichiometry. If here it's written 1, means I have 1 mole. If that is 2, means I have 2 moles reacted. If that is 1, means 1 mole produced. This is the word stoichiometric proportion means. Okay, so let's continue. Then it says that it started at 800 degrees C. So this is the temperature of the reaction. Now you can see that the temperature is no longer 298. So I want to find, according to what they say here, calculate the amount of heat that should be removed from the reactor. And there is an amount of heat that I should remove from the reactor in order to leave the product at 800. What does it mean? It means that this reaction is exothermic, apparently. When the reaction takes place, what will I get? I will get elevation in temperature, but I don't want this elevation in temperature because we need to calculate the amount of heat that will keep it 800. It started with 800 degrees and it should stay. I want the whole reaction at 800 degrees C. I don't want it to change, okay? Because next lecture I will explain what if the temperature changed, and this is the last step. Not the last, but just before the last step of complication, because I showed you the ladder stage. Later on, I will explain what if the temperature is changing from reactant to product. Now here, the question here is delta H naught at 800, and that's it. It is at 800 degrees C. How can I solve this question? We are going to remove the heat because we want, this heat is latent heat. I want to have this heat out of the system without changing the temperature of the reaction. Okay. So the idea basically, first of all, I just want an answer from you. Do you agree that this example is talking about calculating the standard heat at 800 degrees C, and that's why I will calculate the standard heat at 298, okay, Kelvin, and make a correction that is Cp delta T, which is the difference. But on this one, I have to convert it to Kelvin. So when you convert it to Kelvin, then it's going to be 2T, sorry, that's T minus T naught. Okay, and my T naught here is 25 degrees C. I can just put it in degrees C because it's delta, and this one is 800 degrees C. Okay, so do you agree, before I proceed, do you agree that this equation can be implemented here? Because I want to calculate delta H naught at 800, so I calculate delta H naught at 298 and I correct it using this term. Do you agree? Okay, Huda said yes. Others? Can I hear some voices? Ali agrees. Anyone else? You all okay? Okay, wonderful. So if you agree, then we are following this concept. And then the question now, how to get delta H naught at 298? This delta H naught is what? Basically, it is the standard heat for this reaction. Which table I have to use? Is it not appendix C4? If you have your book with you, then you will notice that delta H naught is simply found, as Arwa said, yes, we will find it using the standard heat of reaction. يعني طبعا what I did here, I'll just show you. طبعا you all agreed with me on that. So I'll just clean the screen. Okay, so this is the reaction, and I will apply the equation you just mentioned. Then, before I start the substitution, I will tell you how this equation can be given in a different way. It will be either given as calculate the amount of heat that should be removed so that the temperature is not changing, it's 800 for the reactant and the product, or calculate the standard heat of reaction at 800, which is more direct. The standard heat of reaction at 800 degrees. Okay, so which will lead to the same thing. So that's basically what I wanted to find out. So that's why the way we have to do it, as we said, you have to apply in this equation. Now, T naught, based on the agreement, that T naught is 298 Kelvin. Why? Because this is the reference temperature that I have tabulated. And because of that, I just use the stoichiometric number of each to give the value. So the delta H naught, or the standard heat of reaction at 298, is equal to the standard heat of formation for each species, but I have to multiply it by its stoichiometric number. Then I will sum up all those. يعني the standard heat of formation of CH3OH from the appendix C4, it is this value, and with the minus. طبعا the stoichiometric number it was +1, so you will not be able to see it here. You can just put it as a +1. Okay, then for the reactant, the hydrogen, it is constituent element, so it is 2 into 0, but I put -2 because the stoichiometric number is -2, and for CO it is -1, so it's actually -1 here, that's 1, multiplied by this value, which we got it from the appendix, which is appendix C4. Now, something I will not agree with Smith here, I'm sorry to say this, that one is joule per mole. Okay, well, it's actually joule per mole, but what we did here, instead of using the stoichiometric, it can be that instead of using this stoichiometric number, we can use the number of moles. Still correct, but you will put the sign. Okay, but that's basically, it is joule per mole if I am using what? The stoichiometric number. If you are not using, يعني that is delta H naught per mole of what? Per mole of CO reacted. يعني delta H naught 298, if I want to find it in joule, I will get this value. Okay, this value, it is per mole of CO reacted. Next lecture, I will explain why specifically mole per CO reacted. You can say per mole of CO reacted or per mole of CH3OH produced. Okay, because this is the limiting reagent here. Okay, you can test which one is the limiting reagent using chemistry. Using Ching treble 1. But apparently both will react, both will complete, so I can consider it as limiting reactant. So, and then I have from the information that I have 1 mole of CO reacted. So in this case, the final answer will be same. But Smith did it in one step, that he just put it joule directly. Here I'm showing to you how it will be in joule. It's multiplied by 1 mole of CO. إنزين طبعا with that what we did, we calculated delta H naught at 298. But that's not the end of the story. This only a substitution of the first term. Now I have to find this delta CP mean H. And for students who did, in case you did not get it, I am sure that you will get it now. So what I did, let's say, I need to know how much, if you remember this formula or the CP mean, the delta, I have to use the R into delta A plus delta B over 2 T naught tau plus 1, blah, 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 until the end of the term. So in other words, I need to know delta A, delta B, delta C, and delta D. So what I did, I went to appendix that shows the constants A, B, C, D, okay? And I brought the values written as they are from there. For which species? For the reactant and the product. Look, I have CH3OH, I have CO, and I have hydrogen. The stoichiometric numbers, you can see for CH3OH, it is +1. For hydrogen, it is -2. For CO, it is -1. And this is what I wrote in the first column. And then, as we said, A, B, C, D values were brought from the appendix. And then, I want to clarify a very important thing here. When I multiply by 10 to power 3 here, this means that it is this value times 10 to power -3. يعني in other words, they put this value after they multiplied it by 10 to power 3. But the actual value of B is 12.216 into 10 to power -3. So on substitution, you will take the power that's written here and multiply it, but with the minus, يعني with the opposite. يعني here it was 10 to power 6, it means you will multiply this number by 10 to power -6. Here, you will multiply by 10 to power 5 plus 5. You get the idea? الحين the question here is how to find this delta. Now remember, my CP mean delta is R into delta A plus delta B T naught over 2 tau plus 1 plus higher order terms. But you have to know each deltas of those. So the step here is to get delta, how to get delta A, delta B, delta C, and delta D. And here's the procedure. How did you get those values? I will show you a sample calculation. Sample calculation is delta A. Now, according to the definition, delta A is what? Is the summation of the stoichiometric number into AI. يعني, I will take 1 multiplied by 2.211 minus 1 into 3.376 minus 2 into 3.247. That's basically the value of A. خلاص? Same thing with delta B. It is 1 into, look at that. It is 1 into 12.216 minus 1 into 0.557 minus 2 into 0.422. But keep in mind, you will multiply by 10 to power -3. That's for the B because B is 10 to power -3. And you will be the same thing for C and D. You will get all the values. In this case, you will just substitute. Now here, I use my own programming to calculate CP mean. And for you, if you have a program, that's fine. If you don't, still okay. You will just substitute here of the R as 8.314 joule per mole Kelvin. You would have A, B, delta A, delta B, delta C, D values here. And the T naught is the initial temperature or the reference temperature, which is 298. And tau is T over T naught. And you already have T as 800 degrees C. Keep in mind, you have to substitute it in Kelvin divided by T naught, and all the terms has values. And apart from that, the equation is complicated somehow, but it's just direct math substitution, and this will give you the CP mean. And then again here, he put the CP mean as joule per Kelvin, not joule per mole Kelvin, considering that in his substitution he's using the moles, not the stoichiometric number. I would say it's supposed to be joule per mole Kelvin. So now it just last step, direct substitution. This is 90,135 is this term, which is delta H naught at 298. Here is the CP mean that I calculated, and here is delta T. And the final answer, I will keep it joule per mole. And then the last answer, this is joule per mole, I can multiply it by 1 mole, which is the number of mole of CO reacted. So you will get it as in joule. But this is basically the procedure. I hope the idea is clear. So what I covered so far is how the H is dependent on temperature. So how the temperature, if the temperature is changed, how can I calculate the delta H or the standard heat of reaction at a temperature that is not reference temperature. Now, the floor is open for raising the question. Do you have any questions? I don't think it's a good idea to give any more today. It's going to be too much new. So this 5 minutes, just if you have any question on that topic. And next lecture, I will ask another question. What if something else happened? And we will rectify or find out a solution for any changes in the process. Zain, any question? Are you all okay, guys? Doctor, if use extent of reaction. Yes, Muhammad? طبعا here you did not need to use extent of reaction for a reason, or you didn't need to use material balance for a reason, because if I ask, according to the question, they made it clear for you that you have 1 mole of CO and 2 mole of hydrogen and 1 mole of CH3OH produced. Next lecture, we will make it more complicated by saying, by not putting, you can see that here in the question, they said here it is in stoichiometric proportion. Yani life is easy. That according to what you have in the stoichiometric proportion, this is what we had. طبعا in industry, this might not be exactly the case. You may have like number of moles of CO different, number of moles of hydrogen difference, you have excess, you have percentage conversion, and because of that, you have to make all material balances to know how much in and how much out. Here, they made it easy by giving you how much in and how much out. So that's why at the end, I know I have 1 mole of CH3OH produced. So at the end, the joule per mole was easily converted to joule. Okay, so next lecture, I will talk about industrial reactions. What if I am dealing with real reactions? I will bring real stories from industry where the life is not as straightforward as I said. Yani it's not that 1 mole with 1 mole give me 1 mole, like or 2. I mean, not based on the stoichiometric proportion. That's the idea. So, Mohammed, is this your question? Because you mentioned that if extent reaction is used, then we multiply the total. Well, the joule per mole that you will get, you will multiply it by the xi. Extent reaction means the xi. I will explain that in details next lecture. Don't worry. يعني using extent reaction means how much produced, and the production of the product, it's dependent on the xi and the extent reaction. So that will be covered next lecture. So no worries. Anyone else? Hello? Okay, I advise that during the weekend you start solving problems on these concepts. Okay, whenever you see any question related to standard heat reaction or heat reaction at different temperatures, then I suggest that you solve. I can just give you examples if you want, just to put you in the picture, because I know when you go now you will ask me which one is suitable and which one is not. I can tell you example 421, 420, 422 are doable, and they will be direct implementation of what we said. Okay, I will just give information here. 419, for example, all parts. 419 will be covering next lecture. But if you read 419, you will notice that I don't have stoichiometric proportion. I have percentage excess of air. I have this is more complicated, which is related to industrial reaction, and I will cover it next lecture. But I think giving those 3 questions will be enough for you to understand the concept, or to practice the concept of today's lecture. Anyone else? Hello? Okay, Suad, doctor, can you go please back to the example? Which example? Okay, I'll go back. Is this, yeah. Okay, what is your concern, Suad? Oh, Saud. Oh, sorry. Okay, Saud, what is your question? Hello? Okay, now I wanted the example, but I cannot hear your voice, and I'm not muting anybody, so I don't know why you don't use the voice. Do you want to write your question? Hello? I can't hear any response. Saud, are you around? Hello? Okay, any other question from others? Okay, no more question? Okay, I can see that there's no more question. Saud, if you had a problem with the mic or something and you want to elaborate more next lecture, I have no problem. I can go back to the example and clarify it more based on the question that you were raised. So thank you very much. Have a useful weekend. You need to study chapter 4, and if you really have chance, at least practice 1-2 problems on the part that I covered today, so things are not accumulated on you. Okay, okay, see you on Sunday in this case.